All right. I just need to greet everybody one more time. Hi, everybody. I totally forgot to start recording right at the beginning. So I'm just here answering questions. I'm going through the gas law review sheet. And somebody asked me to just start right away with number 16. So I did, and I forgot to record. So give me a second, and I'm going to show you what I already did. And then I will zip through and do, we've done part A, but we haven't done part B. So it'll be a good review to the people who just heard this. Question 16A was asking for moles. And so that's this equation here. Oh, man, really? That's this equation right here, the PV equals nRT equation. And so what we did is we got the pressure, it was in atmospheres. We got the volume, which was when you measured the room, it was 3 by 4 by 2, which gave us meters cubed. And then I told you that meters cubed is equal to 1,000 liters. I will never give you a conversion that you don't know unless I give it to you. So this problem was a little bit tricky because you didn't know that conversion. So you did 30 meters times 1,000 liters over 1 meter cubed. That's your conversion to get the total liters in that room. So that's your volume that went here. Then we did the N, and that's what our variable was, what we were missing. We did the gas constant that goes with atmospheres. And then we did temperature in Kelvin. We had to convert the temperature into Kelvin. We did all the math, and we figured out our final answer was N equals 1,145 moles. So now we're ready, now that I've started recording, we're ready to do part B, which says, assuming the average molecular mass of dry air is 28.97 grams per mole, what is the density of the air? This time we're going to be using a different equation. We're going to be using this equation over on the side over here. That's molecular mass, which they gave us. Equals density, which is what we're looking for, so that's the variable we don't know, times the appropriate R gas constant times temperature in Kelvin over pressure in this case, pressure is in atmospheres. So I'm going to erase what I've already written because I wrote it so fat that there's nobody can read this. There's no space for me to do the next one. So we're going to do part B right now. And if you just still are working on part A, you can rewind and look at it again. Okay, so for part B, they gave us, I'm going to write on my thing here, they gave us 28.97 grams per mole is the molecular mass. So that's MM in this equation here. Equals D is what we don't know. That's what we're looking for. R is the gas constant. Whoops. R is the gas constant that has atmospheres. Oh my gosh. Get that again. 2, 1. It's hard to talk and do these at the same time. R is the gas constant that has atmospheres. So its label is liters times atmospheres over Kelvin times moles. There we go. And then the last one is the temperature. And we said the temp was 295.15 Kelvin. And that all goes over the pressure. And in this case, the pressure was 0.925 atmospheres. And so now we just solve for D. So to remind you how to solve for D, we want to get rid of everything. Oops, that's not a good color. We want to get rid of everything but D on the right side. So I'm going to multiply both sides by 0.985. So if I were to, I'm just reminding you of your algebra. If I were to, 925, if I were to multiply 0.925 on this side, it would cancel this out. What I do to the right side, I need to do to the left side. So I'm going to add 0.925 atmospheres to the left side. Likewise, I want to get rid of the 0.0821. So I'm going to put that on the bottom. I'm going to divide both sides by 0.0821. So that makes this cancel out. And I'm going to divide this side by 0.0821. So now to figure out what the density is, I now have D all by itself. I'm going to I go ahead and put it into your calculator, 0.925 times 28.97 equals, or I do equals, you guys might not, divided by 0.0821, and we get 326, and I screwed something up. That is not the same answer as what I have written up there. What did I do wrong? Oh, I forgot, you guys, I forgot temperature. Nobody said anything to me. Look at that, temperature's over there. We have to divide by temperature on this side. So I've got to divide by temperature, right? Yeah, divide by temperature, but I don't think I did that on the, oh yeah, I did. Okay, divide by temperature, 295.15. So now temperature goes away and that goes on the bottom here, 295.15. Okay, try it one more time. I'm very sorry about that. So 0.925 times 28.97 divided by, and then in parentheses, you would do 0.0821 times 295.15, close parentheses. And now we get the right answer, which would be, B is all by itself now because we canceled off all the other variables. And then the right answer is 1 point, and I rounded it to 3 sig figs, so 1.11. And in this case, the unit is grams per liter. That's density. So that's our final answer. All right, I kind of made that one confusing. Sorry about that. How are you doing on that last one? Does anybody have questions on that?
Is that always the unit?
No, not necessarily. So it would depend what units. So, okay. In a gas laws problem, yes, it should always be grams per liter. But you can see density in other types of problems. It could be grams per milliliter, or it could be, yeah, it could be other things. For this, it'll always be grams per liter. And that's because your R constant is always in liters. So that's why it's always going to be grams per liter.
Okay.
Okay. Anybody else have a question on number 16? Nothing? All right, I'm going to hop back. I'm going to go all the way back up to number 1. Emma, you tell us if you need anything, let us know. And if you don't, you know, we're all good. I'm going to go back to number 1, and then you guys will just go through it fast and furiously, and you let me know if you have questions, okay? All right. Question number 1, it says a 2-liter balloon. Who's got a guitar in the background? I can kind of hear it. All right, number 1 says a 2-liter balloon at a pressure of 110 kilopascals. So that's a measurement of pressure, kilopascals. Rises in the atmosphere to a pressure of 57 kilopascals. What is its new volume? Assume constant temperature. So I just want to remind you really quickly of, there are 3 laws that we learned. We learned Boyle's law, which is PV equals PV. We learned Charles' law. Charles' law is V over T equals V over T. And we learned Gay-Lussac's, which is P over T equals P over T. You could have them all written down. This is an open note test, so that's your choice. But I'm going to recommend that you just learn this one, PV over T equals PV over T. And that's the first pressure, so it really should be P1, V1, P1. The first pressure, the first volume, and the first temperature is equal to the second pressure, the second volume, and the second temperature in that ratio. If you can just remember this one, that incorporates all these others, and you don't have to worry about the others. And I'll make that make sense in just a second. So I always write down, once I read the question, I write down the equation that I'm going to be using. So I'm going to use this equation. And it says we have a 2-liter balloon at pressure of 110 kilopascals. So I'm going to write that down. Maybe I'll switch up my colors here. So 2.0 liters. I never leave off my units. It's a big deal to just keep yourself straight on what you need to do. And kilopascals, okay? And then it says it has a new, it goes to a new pressure. So here's our new pressure. And the question is, what is its volume? And it says assume constant temperature. So when it says constant temperature, I can ignore this part of my equation. I don't have to put anything down for temperature. So now I'm just doing what's called Boyle's law, which is PV equals PV. This was my, oh, I did it backwards. This is V and this is P, but whatever. That's my volume and my pressure. And now my next one, I'll do it the same way. So we're looking for volume. We don't know volume. And my pressure is, my new pressure is 57 kilopascals. So now I have to solve for V. And just to remind everybody about how to solve for V, you just isolate it. And if you're having problems with your algebra, I want you to be sure to tell me that you're having problems, because then I can practice that with you. But so we divide this side by 57. That makes this go away. So the 57 is gone, and now volume is all by itself. And what I do to the left side, I have to do to the right side. So I'm going to divide this side by 57 kilopascals. And one of my ones disappeared. There we go. So for this first problem, it is 2 liters times 110. So go ahead and put that in your calculator. 2 times 110 divided by 57. And that gives us volume. In this case, volume is 3.86.
Do you know when we're getting our AP Bio test results back?
Such a good question. It's later than usual, unfortunately, because they've scheduled that retake for people who are having technical difficulties. So that retake isn't until June, so they can't get started grading as fast as usual. Although I guess it's maybe a shorter test to grade. But they said July they're gonna be coming out in July. So yeah, it's a long ways to wait, unfortunately. How did you feel about it, Harper? I read your thing. I think you felt like they asked you a lot of questions you felt like you didn't know. Is that right?
Yeah.
Yeah. Yeah. So it was interesting, because it was interesting to do that attendance check-in, because I had a huge mixed bag. People who felt like, oh my gosh, they asked me exactly what I knew. And other people who were like, I didn't know what they were talking about. And so it was really a wide range. What I don't know, Harper and everybody, is how many different questions there were. So Harper, it's possible you got a question that other people would have been like, oh my gosh, I don't know that one. And other people may have gotten a question that you totally would have known, and it was just, luck of the draw. I don't know how many questions they had actually prepared and how many different versions of the test there were. I don't know either. But anyway, so don't, just let it slide off your back and, move on. I'm sorry. It's just a crappy year. It's a very, very weird year. And yeah. So, okay, moving on. Let's get the next one done. As usual, the equation that we're going to work with is PV over T. So I'm going to write it down. PV over T equals PV over T. Now, I started this worksheet with what I think are the easier problems, and they get progressively harder. So these first few are kind of what I think of as the easy problems. So I see it's given me liters, so that's volume. So a 4-liter ball, so I know I've got I know I've got volume, is on a boat under a pressure of 780 millimeters of mercury. So I know that that's pressure, and it says it right there, that's pressure. So we've got P and V again. It says if the boat sinks, what will happen to the volume of the ball? If the new volume is 2.4 liters, what is the new pressure? And in this case, I see again that there's no mention of temperature. So that tells me that this question is not going to be using any kind. Oops, I'm trying to re-log into my computer. Hold on just a second. That tells me that this one is not going to be using temperature at all. So I can cross that part of the equation off. And I'm just going to be using P times V equals P times V. All right, so for the first thing, it just asks what's going to happen to the volume of the ball. As the ball gets pulled underwater, the water pressure is going to start pushing on it, and that's going to cause the ball to get smaller. And now we're going to see that with this new problem. So we had the first pressure. We're going to do P first. The first pressure was 780 millimeters of mercury. 780 millimeters of mercury. And then the first volume is this one here, is 4.0 liters. That's our first volume. Now we want to set it to the second volume and pressure. So we know the new volume. They gave us that, but they didn't tell us the new pressure. So pressure is going to be our variable that we're solving for, and our new volume is 2.4 liters. We want to get pressure by itself. So to do that, we divide both sides by 2.4 liters. That makes this side go away. And we divide this by 2.4 liters. So to calculate this one, 780 times 4 and then equals is the way I do it, divided by 2.4. And you should get pressure is equal to 1,300 millimeters of mercury. How did that go, everybody? Any questions? And Harper, I didn't get a chance to really ask you at all, like if you had done this worksheet or how much help you need. So the at least 2 people told me they just wanted to work through the whole worksheet. So that's all I'm doing. And you can tune in and out as you need and ask questions as need be. So, okay, so the next problem.
Is that in sig figs, KJ?
So, okay, this worksheet, there's a whole bunch of these gas law worksheets that are bad with their sig figs. On my test, the sig figs will be very precise, and it will probably be 3 numbers pretty much every time. So if you're doing 3 numbers, you're going to be fine. But these worksheets weren't written carefully, unfortunately. If you go online and watch most of the videos, almost everybody is talking about sig figs and how many you have and whatever. And these worksheets weren't designed that way, which is really annoying. So we're going to ignore the sig figs on the worksheet, but for the test, for the most part, everything I give you will have 3 sig figs. So that's how you want to do your answer. Who just asked me that?
Sabrina.
Sabrina asked me that. I didn't recognize your voice at first, Sabrina.
How many questions are going to be on the test?
I have not written it yet, but I've got my little outline of what I'm going to do on the test. So I'm going to have, this is my plan. I haven't actually written it. So my plan is to have like 1 story problem that doesn't actually have any numbers in it. It'll just be a question about what you think should happen. Like if we increase the temperature, what will happen to the volume? So I didn't give you any numbers in that. You just have to be able to tell me what will happen to the volume if we increase the temperature. So just 1 problem like that. 1 problem that's a phase diagram, which is on this worksheet, it's question number 14. So at least 1 question about the phase diagram, just reading the diagram and understanding what the phase diagram is talking about. And then I'll have a Graham's law problem, which we'll do in a minute. Actually, it's question number 4 here is Graham's law. Then Boyle's, Charles, Gay-Lussac's combined. So that's 1, 2, 3, 4, 5, 6, 7. So combined gas law. And then 1, 2, 3 ideal gas laws and 1 density. So I would guess the test is probably going to be worth 15 points. That's not written yet, and that's just my approximation. I want it to be more than 10 points, but I don't think I want it as many as 20 points. When you guys aren't with me, able to, get a lot of tutoring and whatever, I don't want to make these huge tests. So we'll say 15 for that one. Okay? Any question about that?
Is the test timed?
Yes, the test always has to be timed just so people aren't, doing tons and tons and tons of cheating.
Okay.
Okay. Yeah. Okay. So we'll move on. The test will probably be about 45 minutes. That's what I'm guessing. And you can take it at 10, 1, or 6 o'clock tomorrow night. Can I just get your feedback really quickly? Those of you that are here, how do those times work? Is that okay? 10, 1, and 6? Do you feel like those give you the choices you need and that you can make one of those times okay?
Yeah, they're good.
They're good? Okay, good. Thank you for that feedback. Because I'm trying to give it for like the right times for everybody. Some people like the morning, some like the afternoon, some need to be in the evening, whatever. Okay, I'm going to move a little bit faster, you guys, so that we're not here all day. Next question. I always write down the equation. PV over T equals PV over T. A balloon has a volume of 2.5 liters at a temperature. Oh, what did I say is the first thing you should notice when you see temperature in Celsius? What should you be thinking?
Change it to Kelvin.
Change it to Kelvin, convert it. So plus 273.15 every time. Never, ever, ever write anything in Celsius for these problems. Yeah, and you're just going to have to trust me on that one. Kelvin is much better. Okay, so it says, what is the new temperature if the volume increases to 7.4 liters? Assume constant pressure. So now for my equation over here, pressure is going to stay the same. So I can just cross off the P's. I don't need to worry about pressure. And now what we're doing is called Charles' law. V over T equals V over T. So the first volume over the first temperature equals the second volume over the second temperature. So the first volume we had was 2.5 liters. So I'm going to write that. 2.5 liters over, and our first temperature is 25 plus 273.15 is 298.15. That's our first temperature. Okay, so then it says we have a new volume of 7.4 liters. So I'm going to write that down, 7.4 liters. And our temperature is what we don't know. And I'm going to write XK for an unknown Kelvin temperature. So now we just need to solve for X. And as far as algebra goes, this is the hardest one to solve for, is when you have one that's down on the bottom. So there's two different ways. There's two different ways to do this one. Some of you might like cross multiplication. That might be easiest for you. And I think that when I was in high school, that is what I always would have chosen. So if you cross multiply, just to remind you, you take one that has the missing variable. So 7.4, you multiply it by 298.15. You divide it by 2.5, and that gives you the answer. So you multiply, then you divide, and whatever you get for an answer, that's the answer. However, if you prefer setting it up without that little trick of the cross multiplication, then let's do that here really quickly just to make sure you know how to set it up. So we want the X to be, I'm going to change colors here. We want the X to be off the bottom of the fraction. So I'm going to multiply both sides by X. So when I multiply both sides by X, I cancel these two X out. They cancel each other out. But now I have X times 2.5 divided by 298. I need to get rid of those. So to get rid of the 2.5, I'm going to divide by 2.5. That makes these go away. And so I have to put 2.5 on the bottom. And then I want to get rid of 298 here. So I need to multiply by 298 on the top. And that makes them go away. So 298.15 on the top. So if you can read through my messy handwriting, what I have is X all by itself, and that equals 7.4 times 298.5, and the whole thing is divided by 2.5. So I'm going to do that right now. 7.4 times 298.15 equals divided by 2.5, and we get 880. And then if it depends how many sig figs, it really should just be 2 sig figs because all of these just had 2. So it'd be like 880. And then the answer was in Kelvin. So that would be your final answer. If you wrote 882, I wouldn't care. If you wrote 882.64489777231, then I'd have a problem with it. But, you know, if you're in the ballpark, I'm not concerned about it. Okay? All right, we're going to try a problem that is completely different. This is Graham's law of diffusion, or effusion, they call it both. And you just need to have this written down. So tomorrow when you go to take the test, have Graham's law, have the notes about how to do that near you. So Graham's law looks like this. It's the rate of the first molecule that we're going to call A over the rate of the second molecule that we'll call B equals, and it's a very wacky equation, the square root, and then you invert them and do their molecular mass. So molecular mass, and you get that from your periodic table. Molecular mass of B over the molecular, do you see that it's upside down? So the rate was A was on top and B was on the bottom. And then with the square root, B is on the top and A is on the bottom. Okay, so we are looking for the mass of H2S and the mass of wintergreen. So I'm going to switch up my colors here, and I'm going to go, here's the square root. And we want, so it says compare the rates of diffusion. So we want to get the mass of H2S. So that is 2 hydrogens and 1 sulfur. and I'm looking on my periodic table to solve that. So the sulfur, it looks like, you should be looking with me maybe, 32.064. So I'm going to type that into my calculator, 32.064 plus hydrogen, and it's got a second hydrogen. So I'm going to do it twice. And we should get 34.08. That's the molecular mass of H2S. So I'm going to write 34.08. Oops. It occurs to me that that's probably supposed to go on the bottom. Hold on just a second, because that was the one I was imagining. I'm comparing the H2S to the other one. So this one was H2S on top and wintergreen was on the bottom. So I need to have them flipped around. So sorry about that. So this would be 34.08 grams of H2S on the bottom. And then the wintergreen, I'll just look at my cheat sheet here because I already added it up once, is 150.133 grams of the C8H6O3. So that the way that I calculated that was looking on my periodic table. I added 8 carbons, 6 hydrogens, and 3 oxygens to get the wintergreen. And now I just do the math on it. So it's just 150.133, enter it in with me, divided by 34.08. And then I take the square root. And you have to, my calculator is one of the old calculators, so you might want to have typed in square root button first and then 150 point whatever over 33. But you should have gotten an answer. Oops, I got to do that now. I got to do the square root. You should have gotten an answer like 2.10 or 2.1. And what that tells us is H2S is 2.1 times faster. This is a rate that we're talking about. HS diffuses 2.1 times faster than wintergreen. That's what that number means. Any questions about that weird one? Anybody? We'll
So
do
if you were in the other
okay.
direction.
Say it again. I'm sorry. Say it again.
So if you were to come at it from saying where wintergreen was, you'd just say wintergreen is 2.1 times slower.
You absolutely could. What would happen if we flipped it around? I just got to look at that because if you did 34.08 divided by 150.133 square root. So you would say, in that case, you could say wintergreen is 0.476 as fast as H2S, or you would say diffuses. Don't worry about the wording. You don't need to worry about the wording, but diffuses as fast as H2S. So it's not as fast as H2S if you did it that way.
So is the lighter one always going to be the faster?
Say that one more time.
Is the lighter molecule always going to be the one that diffuses faster?
It sure is.
Okay.
Good?
Yep.
Yeah, so for that one, just out of safety, I haven't written the test yet, but just for safety, I will have 2 possible answers so that depending on which way you wrote it, whether you put the one on the top or the one on the bottom, I could accept either answer. Okay, let's move on really quickly. I'm not going to spend a lot of time on number 5, but define the following terms. If we were going to define them really, really simply, pressure is the amount of space that's occupied by the gas in this case. So temperature, more importantly, temperature, this is what we call the kinetic molecular theory. Temperature is basically how fast molecules are moving. So a higher temperature just means the molecules are moving faster. If you think about a thermometer, I always think this is such a good little example of what we're talking about. If you have a thermometer that has red alcohol in it, and when it's cold, the thermometer, the amount of red alcohol looks like it's this much. But then as the temperature increase, it looks like there's more and more and more and more alcohol in the thermometer. That's not actually the case. What's happening is those molecules are moving faster and they're spreading out, and it's causing the column of red alcohol to look like it's getting bigger, even though it's not actually even though there's not more molecules being added there. And then finally, volume is the force of those molecules. Oh my gosh, I said that backwards. I did say that backwards, you guys. Pressure is the force. Pressure is the force of those molecules pressing on the force of those molecules pressing on a particular area. And then volume is the amount of space occupied. I wrote that backwards on my answer key. I'm a little bit embarrassed that I wrote that backwards. So sorry about that. So one more time. Volume is the amount of space that's occupied. Temperature is how fast those molecules are moving. And then pressure is the force of those molecules hitting it harder. So for example, if I asked you a problem like, what will happen to the pressure inside of a jar if you increase the temperature on the outside? Say that again. I thought somebody said something. Okay, so if I increase the temperature, then that's going to cause the molecules to move faster. So they're going to hit the walls of the container harder. And so that means that the pressure will increase. The pressure will be greater. If I cool it, then the molecules won't hit the wall as hard. And that means that the pressure will be less. If I did it in a balloon, if I added hot air to a balloon and cold air to a balloon, then the volume would change because it's a flexible container. So if it was cold air, those molecules won't hit it very hard. And so you'll have a balloon that's really small. But if I add hot air, hence hot air balloons, the volume increases and then the balloon itself would get bigger because those molecules are moving faster. Okay, I don't know if that made any sense, but hopefully it did. All right, moving on. Now we're going to really get, these questions are the ones that actually use the combined gas law, which is the full PV equals nRT. We're not going to cross any one part of it off. We're going to do the entire equation this time. So we start with an 8-liter sample, that looks good, of hydrogen at 25 degrees Celsius. Right away, I know I need to add plus 0.273, I didn't say that right, 273.15 Kelvin to make it into Kelvin. And it says it exerts a pressure of 900 kilopascals. That's acceptable. We can do that. If the gas is compressed to 2 liters and the temp is raised to 225, I better add 273.15 to that. What is the new pressure? So I'm going to be looking for P for pressure. I'm going to be looking for P2. So I'm going to write down what I do have. I'm going to write down my P1, V1, and T1 first. So I'll switch up colors. My pressure one was 900 kilopascals. And my volume one was 8 liters. And now my temperature one is 25 plus 273, which is 298.15 Kelvin. That's my first part of my equation. So I've just done this part of the equation. Now I'm going to set that equal to, and our new pressure, we don't know our new pressure, so I'm going to leave that as our variable that we have to solve for. Our new volume is 2.0 liters, and our new temperature is 225 plus 273.15, so 498.15. And then we just have to do the math. We have to get P all by itself. So can I just ask, and I'd like you to speak up for a moment. Are you feeling like you know how to do the algebra and you know how to solve for P by itself? Or is that something that's going to throw you off? Do you want me to keep practicing that, or do you feel like you know how to do it?
We good?
You're good on it? You feel good about your algebra?
Yeah.
Okay, Sabrina, Nabat, anybody else?
I feel good about it too.
Was that Emma?
Yeah.
Okay.
I'm good.
I'm good.
Okay, Sonia,
I think I need a little more practice with that.
you bet. So I'll say it faster each time, and you can tune me out or whatever if you're feeling like you don't need it. I want pressure by itself. So in order to get pressure by itself, I need to get rid of, for example, I need to get rid of that. So I'm going to put that on the top, 498.15. I'll just draw this line longer. When I multiply it on the right, they cancel each other out. But if I do it on the right, I have to do it on the left also. So now I basically moved that temperature to the other side of the equation. I have 2 liters here, and I need to get rid of them. So I'm going to put them on the bottom. I'm going to divide by 2 liters. That makes the 2 liters go away. And what I do to the right side, I have to do to the left side. So 2.0 liters. And I did that to the other side. So now pressure is all by itself. So now I just need to do the math on the left, and I should get the pressure on the right. So entered into my calculator is going to be 498.15 times 900 times 8. I'm going to divide that by, and in parentheses, 2 times 298.15. And I should get around 6,000. Did you get 6,014? Somewhere in that ballpark. So 6,4. And then what's the unit? Well, the unit that we have been using is kilopascals. Kilopascals. Hey, let me give you a quick tip just because you guys are sitting through this. The units on the left and the right have to be the same. So if I gave you pressure in atmospheres at first, and I gave you pressure in millimeters of mercury on the second one, you have to convert them. Either they both have to be atmospheres or they both have to be millimeters of mercury, but you can't have different units on the left side of the equation from the right side of the equation. So just make sure that all your units on the left and the right match. It doesn't matter if they're atmospheres or millimeters of mercury or kilopascals. It doesn't matter, but they both have to be the same on both sides in order for the equation to work. Okay, moving on, unless somebody has a question. It's the same type of problem right now. I'm going to not talk this time. And I would like anybody who's following me to just go ahead and do the problem yourself. And we'll get together at the end. See what you can do. My daughter is practicing her cello in the background. I don't know if you can hear her cello, but just so you know. I'm going to go ahead and work on the problem so you can look up at any time, but maybe resist the temptation.
Damn it.
Are you playing a game, Harper?
Yeah.
I can hear you in the background. What are you playing?
It's like that marble in the ball thing.
Totally. Yep, I could hear it. And your dang it made me know. Oh, what did I just do? Oh, I'm not happy with how I just solved this problem, you guys, because now I have X on the bottom. I wasn't paying any attention to what I was doing. I was just crossing things off happily. I think I'm going to back mine up. I'm going to solve it a little bit differently. So I love that I can just hit back and it all disappears. Are you all done and you're just waiting for me?
No, I'm kind of confused.
Because you're watching me?
No, I got to a point. I always get confused whenever I have to work with scientific notation. And I don't know if I did something wrong, but I entered something on my calculator and now I don't know what to do. So
Oh, okay. Let me finish what I'm doing here. Okay, so I'm going to go ahead and talk you through it and then just see how you did. So I've got X right now on the left and it's on the top. It can never be, the X can never be on the bottom. And hopefully you remember that from math class. So that's why I had to do all kinds of manipulating to get my X above the line on the left side. And now I have managed to cross off everything else on the left side. So X is all by itself. So on the right side, you should be entering into your calculator 0.7 times 0.2 times 500. And I have to hit equals. I'm using this old-fashioned calculator, equals, divided by, and then in parentheses, 0.85 times 0.5, close parentheses. Don't forget to close them. And you should get 164, and I'm just going to double check that that's what I got last time. Yep, 164.7 or 165. So our X equals 165, and that was in Kelvin, right? That's our new temperature, so 165 Kelvin. Emma, how did it go? That was Emma that was asking me a question, wasn't it?
yeah, I tried solving it now
Do you
with
have a different way?
multiplication. So
Say that again.
I tried solving it with just like, I don't know, the not cross multiplication. I don't even know what I did.
So you could, so I'm just thinking of another way that you could solve it. You could have solved it. Let me see if I can use a different color here. So you could have, you see that my original equation was in the teal and then my crossing off everything that was in purple. You could have, let's see if I could solve it for you. You could have done 0.7 times 0.2 equals times 500 equals divided by this stuff on top. So we would have to put those in parentheses, 0.85 times 0.5, those would be in parentheses, and then equals again, and that should give you the answer at the bottom. Is that how you kind of tried to do it, or was it something totally different?
I think so.
There's so many ways. I mean, math is famous for this. It's the same thing with computing. I mean, like working on our computers, there's so many different ways to set up problems. I try to be really consistent and set them up the same way so that students who are learning them just set it up the same way every time. But there are ways that your math teachers have taught you that are alternates that are absolutely correct also. Just as long as you can do it consistently. Let's try, we've got one more problem of that type, Emma. Let's try one more, kind of everybody on their own, and see if we can solve it. So this next one is looking for volume, although this one's on the top, so that makes that one easier. What made this one difficult is just that the X is on the bottom of the equation, and so you have to get the X on the top. But anyway, so let's go ahead and try number 8. Everybody can do it on their own. They are giving us volume, temperature, and pressure. So I know that I'm going to use the PV over T equals PV over T equation. And then it says at STP, and if you don't remember what STP means, it means standard temperature and pressure. And at standard temperature and pressure, it's always 0 degrees Celsius and 1 atmosphere. Atmosphere could also have been measured in millimeters of mercury, which is 760. You don't really need to know that. I won't ask you that. But this is a warning flag. You need to make it 273.15. You have to add that to the 0. So let's see if you can go ahead and set it up on your own. And I'll set it up here fairly quietly. And I'll try to do it in an organized manner. Oh, look at that. Did you notice, everybody, that this is in millimeters of mercury and this one is in atmospheres? So that's a no-no. We have to make sure that we have both of them either in atmospheres or both of them in millimeters of mercury. So I'm going to change mine here quickly. I'm going to get rid of this. Oh, I just erased the whole thing. That's fine. And I'm going to do a little conversion factor on the millimeters of mercury. So 2,800 millimeters of mercury, and I do a conversion, just like you've done in stoichiometry a million times. What you want to get rid of goes on the bottom. So millimeters of mercury goes on the bottom, and what you want left goes on the top, which is atmospheres. So now our millimeters of mercury are going to cross off. For every 1 atmosphere, it is 760 millimeters of mercury. And that's something that's in the presentation and something that could be in your notes that you have handy so that you can convert that quickly. So now it would be 2,800 times 1 divided by 760. And now you'll have your atmospheres. And then you can really begin. How'd that go? Does that make sense, everybody? When you're silent, it concerns me a little bit. It's already 4:12, you guys. Holy cow. I didn't expect to take this long.
So
Sorry. Go ahead.
all the conversions from like the inches and the inches of mercury, the millimeters of mercury, and the kilopascals, to get from those to ATM, it's dividing by a certain factor.
Yes. And so, again, whenever you're, that's why I always do them in the same way, just like we did in stoichiometry. You put your unit that they're currently in, and then you make a line, draw a straight line, and the unit that you're in goes on the bottom so that they cancel each other out. And then the unit that you're looking for goes on top. Yeah. And so what you're looking for is always going to be, and it's always going to be for atmospheres, it's always going to be 1 atmosphere is 760 millimeters of mercury, or 101.3 kilopascals is the other one that it could be. Anything else about that? Should I say anything more? Gosh, I didn't know this would be so long, you guys. I'm sorry. I don't know if I'm helping or making it, if I'm torturing you, but okay. So I'm going to go ahead and work it out here quickly. Pressure is, I'm going to switch colors one more time. And we've got pressure is what we don't know, and temperature and one last color to get V by itself. I'm going to do 273.15 on the top and cross them off. And then I'll pretend I'll do 1 atmosphere on the bottom. Didn't really need to do that since it's just the number 1, but just showing you how you would do it. And now I have V all by itself. And so now 273.15 times 3.68 times 45 equals, divided by 750, and we should get 60. V equals 60.3 liters. I always double check too. I'm sure your math teachers have said this a bajillion times, but I always check to make sure the answer is sensible. We started at 45 liters. Does it make sense that you would end at 60.3 liters? Sure, that seems reasonable to me. So that's a way of me just double checking that I did it right. All right. How are we doing, you guys? Is this going too long? This is going too long. Should we skip a few? You can always look at my answer key. Let's do number 9. Nope, hold on. Number 9 is the same type. Hold on, I'm gonna skip ahead so we can go a little. No, it's not. Number 9 is the first of the ideal gas equation. So let's do number 9, and then we'll do number 12, and then we'll figure it out from there. How about that? Okay, and you guys can always look at my answer key. I posted an answer key so you can look at the answer key, but I don't want to torture you by making this last forever. So let's do this. This first one, how did I know it was the ideal gas law? This is an indicator, the fact that it has grams. When we do the combined gas law, PV over T, there's nowhere for grams. The other hint would be if it said the word moles. Look at question number 10. It has the word moles in it. That doesn't work in the PV over T equation. So that's got to be our ideal gas law. So I always start with the ideal gas law. I always start by writing the equation down. And in this case, the equation is PV equals Nrt. So it says a 500-gram block of dry ice of solid carbon dioxide vaporizes at room temperature. Well, right away, it's a problem because I see it's in Celsius, so I'm distracted. 273.15 plus 273.15. Okay, so what is the volume of gas produced if the pressure is 975 kilopascals? Okay, well, first of all, N is moles, not grams. So I have to figure out how many moles 500 grams is. So that's from our previous moles unit. So what I do in that case is I'm going to write down, I'm going to convert it. I've got 500 grams of CO2. The conversion factors are always the same way. I want to put grams of CO2 on the bottom, and what I'm looking for is moles of CO2. So I put that on the top. That allows my unit of grams to cancel out. So whenever I have grams and moles, it's always 1 mole. So 1 mole of CO2, and then I'm looking for grams of CO2, and that's from the periodic table. So I look up carbon and 2 oxygens. So make sure you add 1 carbon and 2 oxygens. And I'm just going to tell you the number so that we can go a little bit faster for you. Where do I have it? 44.009, it looks like. So 44.009 is the atomic mass of carbon. So I'm going to do 500 divided by 44.009. And I get 11.36. That's how many moles of CO2 that I have. Now I'm ready to actually put it in the equation. So I've got my PV equals nRT. So what's my pressure? My pressure is 975 kilopascals. So P is 975. Volume should be in liters. Oh, we don't know volume. That's what we're solving for. Moles was 11.36 moles CO2. R, now this is the tricky spot. So I'm going to make sure you can see my R there. So this is the part that gets a little bit tricky. This is the gas constant. And I just want to make sure that you remember, if I flip over to a different screen here, that there are different R's. So this little screen says, watch your R units very carefully. So if we were in atmospheres, the R that we would use would be 0.0821. But if our pressure is in millimeters of mercury, then our R changes. The gas constant changes to 62.4. And if you're in kilopascal, whoops, oh, how do I go back? There we go. And if I'm in kilopascals, your R is 8.31. I would have all 3 of those written down somewhere in your notes close by so that you don't have to go digging through presentations or whatever to find them. Just have them handy so that you know which R you're supposed to use depending on what units you're working on. Okay, any questions about that part? Okay, so the unit that we were given for pressure is kilopascals. So in this case, the R that we're going to be using is 8.31. And you don't need to write the units, but I'm going to write the units just so everybody's really clear why I chose that one. And that's because it's the one that has to do with, oops, kilopascals. Why did I write atmospheres? If only you all were as imperfect as me, you would understand my errors, but kPa, there we go. And then the last one is temperature, and the temperature has to be in Celsius, in Kelvin, so 25 plus 273.15. We get 298, oh, I've already done that one a bunch, 298.15 Kelvin. And now we're solving for V. V was all by, we want V all by itself, so this is V here. So to get V by itself, I'm going to divide by 975 kilopascals, and that makes it go away. And what I do to the left, I have to do to the right, so divide by 975 kilopascals on this side. So my answer should be V equals 11.36. I'm going to start entering that into my calculator. 11.36 times 8.31 times 298.15, and then divide by 975. 28.86, 28.87. So V equals 28.87, and that's volume, so that's going to be in liters, always in liters. If I give it to you in milliliters, convert it into liters. How do we do on that one? That's the ideal gas law, so that's the only one that's ever going to deal with grams or moles. It's got to be in moles. If you get it in grams, convert it into moles.
Wait, so how do you know if you're supposed to use the ideal gas law or grams or the combined gas law?
Combined gas law doesn't have grams in it. So on these previous problems where we'd been using PV over T equals PV over T, there was nothing mentioned about grams or moles in those.
Okay.
Good?
Yeah.
Okay. So then, what did I say? We were going to do number 12, I think. Let's try it because I'm trying to give you some of the trickier ones. I know that I'm going to have a problem that has a chemical equation on it where you have to balance it. And it's just simple balancing. I'm not going to give you one that's hard to balance. So let's look at number 12 here. It's going to be another, and how do I know that? It's going to be another ideal gas law, and that's because I see that it's got grams. So right away, I'm going to write down the ideal gas law just to remind myself, PV equals nRT. Okay, so it says how many liters of ozone, which is O3, can be destroyed at 220 Kelvin, good temperature, and 5 kilopascals. Oh, I got to use the R constant that has to do with kilopascals. If 250 grams of chlorine gas react with it according to the following equation. Okay, so notice that it's asking for ozone, but it's giving me chlorine gas. That's a little bit of a problem. They need to be the same. For the ideal gas law, it has to all be the same molecule. So in that case, we are going to have to use our stoichiometry to figure out how many moles of O3 we're dealing with. So first thing I'm going to do is balance the equation. So right away, I see that I have 3 oxygens on the left, 3 oxygens on the right. But I have 2 chlorines on the left. So I'm going to balance this by putting a 2 here and a 2 there and see if that worked. I now have 6 oxygens. I have 4. Nope, that didn't work. So now I need to add 1 more 2 right here. And now it looks like it's totally balanced. I have the same on the left and I have the same on the right. So now this is a problem where I would give you, this is worth more than 1 point because this is a couple step, 2 or 3 step problem. The first thing I'm going to do is write down how much chlorine gas I have. And I'm going to convert that into, and it's actually going to be 2 steps. I'm going to convert that into moles of O3. So this is where the stoichiometry comes in, and this is why we do stoichiometry before this unit. So I'm going to put grams of Cl on the bottom, moles of Cl on top. And whenever we have grams and moles, it's always 1 mole. And then down on the next one, I'm going to put moles of Cl on the bottom and moles of O3 on the top. And whenever we have moles and moles, that's the mole ratio. And that's where I get to use the coefficients. So, sorry, I wrote Cl. It's Cl2, you guys. I'm sorry. I'm being sloppy. So Cl2 only has a 1 for a coefficient, so I'm going to put a 1 there. But the ozone has a 2 for a coefficient, so I'm going to put a 2 there. And then the only thing I have left is my atomic mass, and that's what I get from the periodic table. So I'm going to look chlorine up, and it is Cl2, so I have to multiply it by 2. So chlorine is 35.453 times 2 is 70.906. 70.906. So now that's going to give me my moles of O3. So I'm going to multiply it out. 250 times 1 times 2 divided by, in parentheses, oh, it didn't really need parentheses, but yes.
Is the equation going to be balanced on the test?
I wasn't planning on it, no, but because I don't want it to be anything really tricky, but you should be able to balance it. I don't know. I haven't written it yet, so I don't know. Are you worried about it, Sabrina?
Yeah.
I don't want it to screw people up. Like it's not what I'm testing. What I'm testing is your ability to do the ideal gas law, not your ability to balance, but it kind of all is a package. It's, can you do the whole thing? So I can't promise. There might be one balancing equation on it. Okay. And it won't be a hard one. It'll be like you put a 2 or something like that. It shouldn't be a big deal. Okay. Let's say this, for those of you that are here with me, if you decide that you're worried about taking the test in the right amount of time, it'll probably be 45 minutes, maybe longer. If you're worried about that, you can take the test with me instead, but I want you to let me know. And then it won't be timed. We'll just do it in a Google Meet, and you'll work on it while I'm sitting here doing my work, and then you don't have to be timed on it. Okay, how's that sound? So if you feel like you need extra time, if you're worried about the timing, just take it with me. Okay, I'm going to move on. So the right answer for the moles of O3, I just want to make sure that it agrees with my original answer key. For moles of O3 should be 7.05. And yep, that's what I got. So I'm going to change the color so it jumps out at us. 7.05 moles of O3. Okay, so now I have moles of O3. That's this part of the equation. That's the N in the equation. And now I'm pretty close to ready to use the PV equals nRT equation. So we've got pressure. Pressure is in kilopascals. So that's going to be 5.75 kilopascals. Volume is what we're looking for. It says how many liters. So I'm going to leave that as a variable V. And then N we said was the moles, 7.05 moles of O3. Now the R, we need to use the correct R, and this R we need to use is the one that's with kilopascals. So if I can't remember which one that is, then I have to look it up. In this case, it happens to be the same one that we did with problem number 9, which is too bad, but it's 8.31. So that's R, and that would be liters times kilopascals over temperature times moles. And then the temperature here was, what was the temperature? I can't find it. There we go. 220 Kelvin. We don't have to convert that one. Okay, so we have volume. We want volume by itself. So to solve for volume, we're going to divide this side by 5.75. That makes it go away. And we'll divide this side by 5.75 kilopascals. And when I enter it all in, 7.05 times 8.31 times 220 divided by 5.75. And we should get a fairly big number, 2242 liters. And let's see, so V equals 2242 liters would be our final answer. Okay, how's that, everybody? What we have left is basically the same problem. So number 13 is almost identical. In fact, virtually identical. You just need to balance the equation and then do your stoichiometry first and then enter it in. However, notice that this one is in millimeters of mercury, so you're going to use a different R. You're going to use an R constant that reflects millimeters of mercury, not the R that you used up above, which reflected kilopascals. And then if we go over to, oh, this is the last thing, and then we'll be done, you guys. I'm sorry this is taking so long. Study the phase diagram to the left, identify solid, liquid, and gaseous stages. So solid is here, liquid is here, and gas is here. If you're not remembering this, then go to the phase, I think it was called heat and phase diagram screencast, something like that. Identify the triple point. That's this right here. That's where all three phases come together. So they're all present at the same time. So you could have, if this were for water, if this diagram were for water, this, whoops, water, this would be ice. Ice would be here. Water would be here, and water vapor would be there. And they all three exist at this point right there. That's called the triple point. What should each axis be labeled? So temperature is on this one and pressure is over here. Figure out where the boiling point and melting points would be at STP. So STP, standard temperature and pressure, would be like 1 atmosphere. So somewhere on my chart tomorrow, I'll have 1 atmosphere. So you would go like this and straight down. So where it intersected this line, that's the line between solid and liquid. And so that's the melting point. So that would be right here. That would be the melting point down there. And going straight across from 1 atmosphere where you intersect the next line, going straight down, that's where you're going between liquid and gas. So that's the boiling point, would be right there. And then finally, it says, where is deposition and sublimation? The reason I ask that is because those are new words for most people. Deposition is when a solid becomes, I'm going to switch colors so you can see a little better. Deposition is when a solid becomes a gas in one, that's sublimation, is when a solid becomes a gas. That's what happens to your ice cubes in your freezer. Have you ever noticed that ice cubes get small over time? They are going straight from a solid into a gas without melting. They don't melt in your freezer. They just go straight to gas. That's sublimation. The exact opposite can happen when a gas goes to a solid. And that's what happens in the winter when we have water vapor in our air, humidity in our air, and it touches a cold window and it freezes instantly and you get the frost forming on a window. That's called deposition. That's when it goes from a liquid to a solid. Condensation is when you go from a vapor to a liquid. So that's condensation. Vaporization is when you go, did I say that? I said that backwards. Condensation is when you go from a gas to a liquid. That's condensation. Vaporization is when you go from a liquid to a gas. Blah, blah, blah. I think that's about it. You know what melting and freezing are. That's this one here. So melting would be going from a solid to a liquid, and freezing would be going from a liquid to a solid. Okay, weirdos. I left you some that you can still work on. So like number 15 is a density one, and that'll be like number 16. And then the ones on this other page that we left blank, those are like ones we've already done. So you should be able to try those. And then look at my answer key because my answer key has it all spelled out. Okay? Oh my gosh, I'm so sorry this lasted so long. Does anybody have any questions? I'm going to go ahead and close things out. Does anybody have any questions for me before we go? Okay, if you want to take the test with me tomorrow, like you're just going to work on it with me, let's do it at Nabat. Nabat and Sabrina, do you guys have prayer time at 1? Can we take it at, if you were, I don't know if you even want to take it with me, but if you want to take it.
We have it at like 1:10, I think so.
Okay, that's a terrible time. What's a better time for you if you want to? You might not even want to take it with me, but
4 o'clock.
Nabat, how is 4 o'clock?
It's good.
Should we do a test with me for anybody who wants to not be timed at 4 o'clock tomorrow? Okay, so you do not have to do that. You do not, but email me if that's something you want to do. Sonia, if you want to test with me, email me and let me know that you want to do that, and we'll aim for 4 o'clock. Okay, so that will be an untimed test for anybody who doesn't want a timer.
Okay.
Okay, everybody? Anybody have any
Yeah.
last minute questions? Okay, I'm sorry this was so long, you guys. Have a good evening, and I will see you tomorrow, or I'll see your tests tomorrow. Okay? Have a great day, everybody.
Thank you, KJ.
You're welcome. Bye.
Bye.
Oops, screwing this all up.